For the second half of the day, we have a series of presentations that evolve around the testbeds themselves. We'll introduce each of RICAIP's testbeds, which are not just the 2 floors here in the building in Prague, but also at our partners in Brno and in Saarbrücken. And we will start with a presentation from Professor Müller from ZeMA in Saarbrücken, presenting RICAIP's Saarbrücken testbed. Thank you.
Thank you, ZeMA, for your kind introduction. So I'm proud to present here actually now our activities at the Saarland at ZeMA in Saarbrücken, where we have a close relationship to also the DFKA with my colleague Walster. I will give you in the next some minutes a small insight into our activities there. Of course, I think this was shown today several times where our location is. This is near France, near Luxembourg, in the southwest of Germany, where both institutes are located. ZeMA itself is divided into 5 different research fields. Here for us today, I think the middle 3 are most important because they are directly addressing production. This will mean manufacturing technologies, what we saw also today here in the test labs, and where we have heard some reports this morning about some success stories where we have new research and new results achieved in the last years. Industrial security and energy efficiency is, of course, today very important, especially if we are sending our data into other regions, into other plants, in a network of plants and so on. There it is always a danger that somebody is coming into your network and make some damages in your facility, and especially in production. Of course, this is very, very unfriendly and very expensive to stop the production because of those guys. I personally am responsible for the assembly systems inside of the production. This is, in my opinion, one of the complicated areas because all failures made before are running in there. And if you have any problems in regards to quality and processes, often the reason is in manufacturing and in, for example, missing parts. And this is what my colleague this morning mentioned. The synchronization between assembly and delivering of parts in the intralogistics is very important. And this, of course, could be enhance the performance there in the future, especially also in using some artificial algorithms to assist there in these very complex situations. Especially because we are dealing today not with very easy products, we are dealing with a lot of varieties of products, so that the sequencing and the strategy in parts delivery, especially in regards to just-in-time and just-in-sequence procedures, are very important in order to not to stop the production because of some delivery or assisting errors. Our story begins in the start of operations at ZeMA in 2012. Soon after that, we started the collaboration with the DFKI in creating the first Industry 4.0 project German-wide. And on top of that, we then founded, and we saw it this morning already, the so-called Power for Production Consortium, which is running until today and was the basis of some other activities like, for example, the Mittelstand 4.0 Competence Center that is located in the Saarland. We have some others in Germany, and yeah, of course, actually the European Union takes this as a success story and actually has some calls out there to install those centers also European-wide in other countries. So this is a success story of Germany. After that, we are talking a lot of cooperation, and especially about production networks, and this was one of the basic ideas of RICAIP that starts in the second phase, as we heard it this morning, in 2019, and we are proud to be part of it. If we are now going to the activities of ZeMA in regards to this project, to the RICAIP project, then we see our main activities here in digital factory and automation systems. What we try to increase, we want to develop something like it is called digital twin of the factory system, and use this as a help for automatization of processes inside the factory itself. Of course, we have to plan our production, not only the production program, but also the production devices and the equipment itself. This is also done with the assistance of digitalization to bring in with these simulations, for example, activities like industrial robots and especially human-robot collaboration. This is one of our main activities. We have seen this this morning in the videos when we have this live video out of Saarbrücken, where some activities and some demonstrators were shown in action, and it was only some of these demonstrators. We have much more activities, but this would lead to too much time consuming here in this context. For me personally, of course, the change of automotive industry is very important in the next years, not only e-mobility, but especially hydrogen that is slowly coming in the cars more and more and more. And there I see a big future in zero-emission drive technologies. And another problem is the production of autonomous driving cars, yeah? Because there are a lot of ideas in the research and in the prototype building of the car manufacturers, but they are not usable systems, and especially also regulations from the government and regulations for producing the cars to making it sure that from kilometer zero they are functioning. There are no existing processes, and this is one of our research activities. If we are now going in, what are the research topics? There are some, and maybe I can tell you also some examples. Yesterday we were asked about, you're always telling these success stories, yeah? But do you have also stories what is going wrong? Yeah? And here we can, for example, go to the human-robot collaboration. There was a big hype cycle the last years. Everybody is speaking about hundreds of unemployed workers and so on. 100,000, 200,000, 300 robots will be installed, and nobody has any work anymore. So we go with a big car manufacturer to that thing, because they were very excited about, come on, let's bring robots in our production. This was together with Ford St. Louis. They have a big production. The normal production rate is 1,800 cars per day. Today, of course, they have problems. They are not producing 600 a day. But we try to look in that factory and make a little searching for possible cases. We are running through the plant to the final assembly and see more than 200 stations there. Big potential, we thought. Yeah? So we go deeper in, and we found in these more than 200 stations 12 possible cases, what we identified. Then we looked to the technical thing. Is it technical-wise possible to bring in an automatization? We had only 6 cases where it was technical-wise sensible. Next step, cost. Does it make sense in regards to cost to install a human robot collaboration? Remaining 2 cases. So we found out of more than 200 stations, 2 cases where it is possible, cost-wise and technical-wise, to install these robots. We planned it out, and then they come to the decision, we have no technicians to serve and service these stations in their life cycle, and so we decided not to install one. Yeah? And this is a point you have really close to look at use cases and where does it make sense and where does it not making sense. And a success story is all the time there where you increase ergonomics and where you can parallelize the activities, because it makes no sense that the robot works and the human stands still, or the human works and the robot stands still. And these are special cases if you look with this view on that things, then you find, of course, several applications in industry, and we have installed already more than 10 only we. Digital data planning, data engineering, digitalization, another example. We have a close relationship with Festo, dealing on pneumatic technologies, especially producing pneumatic cylinders. And they ask us to go in to analyze their production and to get out the data, analyze the data, and try to increase the quality. Catastrophe, absolutely catastrophe. We had lots of data, about 1,000 cylinders, all the data of the machine. And then we try to analyze the data. First of all, we see the timestamps of the data were not okay. The machines were not synchronized. Every station has another clock. So we worked on this problem some weeks to synchronize that. Then we see, the counter in the stations are overflown. This means they count from 1 to 1,000 and start again with 1. But what will you do when you have the data of 20,000 cylinders? You have 20 times, 20 times the number 1, the number 2, the number 3, but what is what now? To be honest, it took us several months to bring the data to a good standard. Then we bring in our advices in their machines, and after that we are starting again to collect data and analyze it. This was a time period of about half a year. Now we got data that are synchronized and where we find to which cylinder it fits and so on. And we're very happy, my assistants and the assistants of a colleague, to find out that we found 4 clusters. We are looking for patterns, what fits together and so on, and we have a good picture of what we presented, and there are 4 clusters in there. And I'm sometimes a little bit unfriendly. I ask my assistants, why do we have 4 clusters? Why not 3? Why not 5? No answer. Okay, I accept 4 clusters. What does these 4 clusters mean? What's the question? What does it mean? What knowledge can I take out of that? 4 clusters, what does it mean in regards to quality, in regards to what? And this, of course, leads then to the thing that if you always put data in and in and in and in, and don't ask what data you put in, you get no explanation what you found out. So explainable AI. This is a case, this is a reason. And we discussed also with several other people on this thing, and especially also I have seen here some ABB robots, and with the chief developer of ABB, he explained that what you can do conventional, please do conventional. And only that, what remains, you can solve with your AI algorithms, and then you have the chance to explain what the solution will mean. And this, I think, is a very important knowledge, what we want about these several projects inside, and where we be able to bring in some sensible applications. And I see DFKA is also doing in some different cases, but with a background of what can go wrong. Maybe, if I have the time, a last example. Daimler has made a challenge worldwide about collecting out of the S-Class production in Stuttgart-Sindelfingen, and they put out the data of 10,000 cars. The problem was often the wheel alignment was not correct, and so they put all the data out of their production, the axle assembly, the underbody assembly, the end-of-line data, and so on. The challenge was over after 2 months. A young boy, or a young man, 18 years old, won this. He was increasing his hit rate from 68% up to 78%, and so far he was the best. He got 25,000 euros from Daimler. Daimler then tests the data and took the next 10,000 cars. Hit rate 65%. So, is it good? Is it bad? So I have experience in car production. For me, it's a little bit better than guessing, because if you guess, you will come to 50%. I have 10 years experience in car production. I would say on the first day I would find more reasons than this algorithm. The point was they have not looked at the data, which data they put in. Yeah? One of the special results was, especially the red cars have a misalignment on their wheels. So, why red cars? They thought, yeah, measurement technology, maybe measurement technology. But I know from my experience, red is not a color that is difficult to measure. Black is a problem color. But why red cars? Very simple if you think about. These red cars have a sport transmission because sport cars are over the mean red. And the sport transmissions are very sensitive to install. This was the explanation and not the color red. Yeah? This to the experience of some projects we have made and the things what we learned and bring in all these activities here. And if you look to that, then you come to a sensible AI in production where you really can increase efficiency, where you can increase quality and so on. So this some short stories motivated out of the comments from yesterday and our activities here. Now I will show you our testbed itself. Here our production line for the final assembly of cars, some production lines, what we also part-wise developed together with the DFKA, where we assemble smaller products, where we bring in our knowledge in there. Main application areas are for us automotive industries and suppliers of these, first-tier and second-tier suppliers, aircraft industries, and they're also the suppliers, for example, not only Airbus, but also Premium Aerotech and so on. And of course, special machine suppliers, because these are the guys who develop and construct the machines with which you produce. And these are those guys who bring in the sensors and the data out for our algorithms. So, therefore, it is very important. Yeah, here another view in our facilities, especially automotive production, and some things out of human-robot collaboration. This was an application in regards to the aft section assembly. Yesterday we had heard something about a wing assembly out of Bremen. This is Premium Aerotech in Augsburg, where they have the aft tail production and the floor grids of aircrafts. Very complicated, very unergonomic, where we have found out some really good applications where we save not only time, but where we also prevent the health from the workers in regards to avoiding unergonomic solutions. Good. This is a short overview about different applications. This we have seen this morning in our videos. And so far I will close my short speak on the presentation of our testbed and wish you a good day. Thank you for your attention.